Okay, this section of the lesson comprises of a lot of calculation, and it's a little bit studious. So the attention has to increase. For this case, ever since we have just been calculating the equilibrium constant Kc for reaction when the concentration has been given to us, but they didn't tell us if the reaction is at equilibrium or not. But in this case, we are going to write one, the balance equation, determine the value of x, and with that value of x, we determine the concentration. On the layer concentration, I will determine the equilibrium constant Kc. So I'll give you an example, and with the example, I'm going to teach you how to actually come about this type of question for equilibrium constant for reaction that's attain equilibrium. Example. Calculate the equilibrium constant Kc. So let me read the equation for you. The equation goes thus: 2 moles of nitrogen reacted with 1 mole of hydrogen to form ammonia. At equilibrium, the number of moles of ammonia was 0.2 moles. Full stop. The reaction took place in a 2-liter container. Calculate the equilibrium constant Kc. Calculate the equilibrium constant Kc. The question is very tricky. So for some of you, you'll just be taking this number of moles that I've been giving to you. You divide by the volume, and then you have your condensation. And you apply the formula, which is very wrong. Why is the question tricky? At this level of the question, the reaction at equilibrium. So this is what equilibrium, very important. At equilibrium, the number of moles of ammonia was 0.2 moles. Then we have two conditions here. We have the number of moles of ammonia before equilibrium. We have the number of moles of ammonia at equilibrium. So we move our data from the question. So let's remove the data. So N of N2 equals 2 moles, 2 moles. N of H2 equals to 1 moles. At equi, N of ammonia equals to, at equilibrium, equals to 0.2. The volume is 2 liters. So having our ingredient, we'll go forward now to solving the question. The first step is to write the balance equation. So the pioneer in chemistry, so talk about chemistry, everything has to be resumed on a balance equation. That's why I say chemistry. So let's go to the resolution of the example. So the equation goes thus: we have N2 gas plus 3H2 giving ammonia. Ammonia. Before equilibrium, before equilibrium, in some textbook, you guys will see initially. You can say initially or before equilibrium. So before equilibrium, we are going to take the number of moles. The number of moles of ammonia is 2 moles of nitrogen. Sorry. Hydrogen is 1. Ammonia is 0 initially. At equi, this number of moles of the reactant will drop by a stoichiometric coefficient. So the number of moles of the reactant drop. Why? Because reactants are converted into products. When the number of moles of reactant drop, the number of moles of the product increase. Why? Because reactants are converted to product. In this case, we have at equilibrium, we have 2 moles. That drop by is stoichiometric coefficient. The coefficient is 1. So we cannot just say 1x. 1x is tautology. So we just say 1 times x is x. So we just say x. The number of moles here is 1. The coefficient is 3. So you're dropping by 3x. The number of moles here is 0. We can't say minus. Why? Because ammonia is already a reactant. At the reactant level, the concentration of the reactant is increasing. That's why we're not using a negative sign. So reactants are increasing while products are decreasing. That's why reactants have negative sign. So here is plus the stoichiometric coefficient, which is 2x. But remember what they told us. At equilibrium, the number of moles of ammonia is 0.2 moles. In that case, I will make x the subject of the formula. It simply means that at equilibrium, this number of moles of ammonia is 0.2. It simply means that 0 plus 2x is equal to 0.2. So 2x equals to 0.2. It means x is equals to 0.2 divided by 2. X is equals to 0.1. X is 0.1. What is the physical significance of that? It means that we are going to look for the number of moles at equilibrium of nitrogen, the number of moles at equilibrium of hydrogen, given that we already know our value of x. So let's find the number of moles of nitrogen and hydrogen at equilibrium. We need not to find the number of moles of ammonia at equilibrium because it has been given to us in the equation. So in this case, remember that for nitrogen is 2 minus x. So having 2 minus x. X is what? X is 0.1. Having 2 minus 0.1. So the number of moles of nitrogen equals to 1.9 mole. Number of moles of hydrogen equals to 1 minus 3 into 0.1. 1 minus 0.3, which will give us 1.7 moles. Beautiful. So we're going to take this data somewhere because I have to wipe the board. I'm going to take this data. The data are the number of moles of nitrogen, the number of moles of hydrogen, the number of moles of ammonia, even though ammonia was given to us ever since. So let me take the data because we'll use the data to calculate the concentration. Data. Number of moles of N2, 1.9 moles. Number of moles of H2 equals to 1.7 moles. Number of moles of ammonia equals to 0.2 moles. Volume is 2 liters. So let me wipe the board. We'll continue with the solving. Remember that Kc stands for the concentration of the product raised to their coefficient divided by the concentration of the reactant raised to their coefficient. With Kc, we are not dealing with number of moles, but we are dealing with concentration. So once you calculate the number of moles of each guy present in the mixture. So let's calculate the number of moles. The concentration. So concentration of N2 equals to, remember, concentration is number of moles over the volume. The number of moles is 1.9. The volume is 2. Concentration of H2 equals to 1.7 divided by the volume 2. Concentration of ammonia equals to, the number of moles is 0.2. The volume is still 2 because this reaction is taken in a 2-liter container. So punch our calculator. We have 1.9 divided by 2. 1.9 divided by 2. So here we have 0.95 molar. Concentration of H2 equals to 1.7 divided by 2. 0.85 molar. Concentration of ammonia 0.1 molar. Apply the formula for Kc. Kc is equals to concentration of ammonia square divided by concentration of N2, concentration of H2 cube. So apply the formula. Kc is equals to concentration of ammonia 0.1 square divided by concentration of N2 0.95 into concentration of H2 0.85 cube. Kc equals bracket 0.1 square divided by bracket open 0.95 times 0.85 and 0.85 0.85 cube. So up to 0.1 and 0.1. So here we have 0.01 divided by 0.95 times 0.6 what? 1/4 times 0.95 0.59. So I have 0.016 Kc. 0.286. And here in this case we are going to like look for the unit there. So here we have a square. So you have there 1 times 1 plus 3 is 4. So here is 2. So having 4 divided by 2, which is 2, we are left with mole square or per mole square, because per mole square gn to the 6. So that's the unit. See, the exercise was actually a complex one, but we succeeded to have the answer to the exercise. So now we're going to see, actually we're trying to see the equilibrium constant Kc for reaction that attain equilibrium. Then we not just have the equilibrium constant Kc, we also have the equilibrium constant Kp. The equilibrium constant Kp is relevant for reaction that involve gases. In that case, we'll be dealing with partial pressures. So partial pressure is not a new notion. When we're seeing phase equilibrium, we spoke about partial pressure. We said that the partial pressure is the pressure exerted by a vapor on its own liquid when both has attained equilibrium. So when I has attained equilibrium means that the rate of forward reaction equals the rate of backward reaction. That means the rate at which a liquid is converted to vapor, the vapor is also converted to liquid. So now we'll be dealing with the partial pressures. So we'll see the equilibrium constant Kp for reaction involving gases. So other topic 3, the chemical equilibrium. I'm going to see the equilibrium constant Kp. We saw the equilibrium constant Kc. There's a relationship between Kp and Kc. I'm going to give you the mathematical relationship at the end of the class. Then, have the equilibrium constant Kp. The equilibrium constant Kc, as I said earlier, is mostly involved with gases. So, consider the reaction below. So, the reaction is N2 gas plus KH2 gas. The recipe reaction giving 2NH3 gas. The equilibrium constant Kc or Kp is not, they are not quite different. Just how with Kp will be dealing with the partial pressures. So apply the formula. Ep is equals to the pressure of ammonia squared divided by the pressure of N2, the pressure of H2 cube. But remember from our equation, the Paulin equation, we know that the partial pressure of I is equals to Xi times P total. Where Xi is the mole fraction, P total is the total pressure in the system. In this case, our system consists of nitrogen, hydrogen, ammonia. So we have to know the pressure of ammonia in the system, the pressure of hydrogen in the system, the pressure of nitrogen in the system. So from the equation, we make use of the separate equation. For ammonia, the coefficient is 2. That's why the pressure is square. The coefficient for NH2 is 3. That's why we cube the pressure. The coefficient for nitrogen is 1, but we can't just say P to the power 1. For anything raised to the power 1, that's same thing. Then from the board, if we just say like this, I will not do an example, that's if I've done nothing. So let's see an example, or let's have an example on the board. Example, a system is made up of 2 moles of nitrogen, 1 mole of hydrogen, and 3 moles of. So here we have the made up of 2 moles of N2, 1 mole of H2, and 3 moles of NH3. The total pressure is 3 atmosphere. Calculate the equilibrium constant. Calculate the equilibrium constant Kp. So let me read the example for you guys. Example. A system is made up of 2 moles of N2, 1 mole of H2, and 3 moles of ammonia. The total pressure is 3 atmosphere. Full stop. Calculate the equilibrium constant Kp. The first thing to do is to write the balance equation. The balance equation here is between N2, H2. So here we have N2 plus 3H2 giving us 2NH3. So we know from the general equation the partial pressure I is Xi times P total. Q total in this case is 3 atmosphere. So our main aim here is to determine the partial pressure of N2, partial pressure of H2, and the partial pressure of NH3. So let's calculate the partial pressures. So partial pressure of N2 is the mole function. So let's check the mole function of the mole of N2 in the system. We have 2 divided by the total number of moles. We have 2 moles plus 1 mole, that is 3 moles already, plus 3 moles again, that is 6 moles. That is 6 times 3. The partial pressure of N2 is equals to 2 times 3 is 6. Divided by 6, 1. So here we have 1 atmosphere. So that's the partial pressure for N2. So I need to write both in order to calculate the partial pressure of the other guys in the system. So let me write both. So partial pressure of H2 is equals to the number of moles of H2. We have 1 mole boost in the system divided by the total. The total number of moles is 6. So 6 moles. 6. All that times 3 because 3 was the total. So here we have half, that is 0.5 atmosphere. The pressure of NH3 is number of mole. The number of mole is 3 for NH3 divided by the total. The total number of moles is 6. Why 6? Because 2 plus 1 is 3 plus 3. That is 6. Times the total pressure times 3. So here we'll have 3 cancel. 3 goes here 2 times 3 here 1. So I have 3 all over 2. So let's punch in our calculator. 3 all over 2. 9 divided by 6. So 1.5 atmosphere. So given that we already have all our pressures, we have the pressure of nitrogen, pressure of ammonia, pressure of hydrogen. We can peacefully apply the equilibrium constant case. Applying the equilibrium constant case, we're gonna have. So let's apply the equilibrium constant case. Kc is equals to, or Kp is equals to the pressure of the product. The product in this case is ammonia. So you have pressure of the product, which is NH3 square pressure divided by the pressure of the reactants. The reactant here, we have 2 reactants. We have nitrogen, we have hydrogen. So nitrogen, the coefficient is 1. So divided by pressure of nitrogen, coefficient 1. Pressure of hydrogen also, the coefficient is 3. Pressure of hydrogen, coefficient is 3. Kp is equals to, so let's apply the formula. So the pressure of ammonia, let's look for ammonia. Ammonia 1.5 square divided by pressure of nitrogen. Pressure of nitrogen is 1 atmosphere. There just put 1. The pressure of the other guy, hydrogen, 0.5 cube. So we have to punch in the calculator. Pressure equals to, so 1.5 square. 1.5 square equals to 2.25. 2.25 divided by 0.5 cube. 0.5 0.5 and 0.5 0.125. Kb is equals to 2.25 divided by 0.125. 18. So we have to look for the unit here. So is going to be per atmosphere square. Per atmosphere square. That's the equilibrium constant Kc. So for the equilibrium constant Kc is not as studious as that of Kp. The one of Kc is not as studious as that of Kp. Then, what's the relationship now between Kc and Kp? Why are we even studying the equilibrium constant Kc? The equilibrium constant Kc is applied in industrial domains such as the pharmaceutical science, the industrial domains such as the production of cement, paints, and all the rest. Why is that chemists are interested with the equilibrium constant Kc? Because for you to run a large scale production, you have to know the constant at which the reaction will be proceeding. Is it at 30 liter per second? Is it as 50 liters per second? What are the factors that will be important to increase the yield of a business? You know, a businessman is out to make profit. For you now to satisfy a businessman, you need to give him the various parameters for his reaction to occur or reaction to be best. Will the reaction be suitable at higher temperature? Will the reaction suitable at lower temperature to maximize the yield? So that is why we study the equilibrium constant Kc or Kp. So the relationship between Kc and Kp goes thus. Let me give you the relation report. Relationship between Kc and Kp. The relationship between Kc and Kp is summarized using an equation. The equation goes thus. Kp is equals to Kc into RT delta N. What Kp stands for the equilibrium constant for gases, Kc, the equilibrium constant for aqueous solution, R is the ideal gas content, T is the temperature in Kelvin, delta N means the change in number of moles. So let me put the value. R is 8.31. T is temperature in Kelvin. Delta N is change in moles. Change in moles. So what does that mean? They can give you a reaction where they give you case. They ask you to find Kp, but they don't give you actually the concentration. So, but if you know the temperature and the change in moles, actually you'll be able to calculate Kp. So let's take a typical example. Consider the reaction below. Consider the reaction. So consider example. Consider the reaction. Consider the reaction. N2 plus O2 giving NO2, two of them, two here. Kc for the reaction equals to 10. Calculate Kp at 100 degrees Celsius. So let me read the example for you guys. The example goes as, consider the reaction. The reaction is N2 plus 2O2 giving 2NO2. Kc for the reaction is 10. Calculate Kp at 100 degrees. Let me calculate Kp at 100 degrees. But in this case, the data for what was been given some data, we have Kc. So Kc is 10. Temperature. So remember that we have to convert the temperature from degrees Celsius to Kelvin. So we have a temperature of 100 degrees Celsius plus 273. So it's going to give us 373 Kelvin. R is a constant, 8.31. So R is a constant. Hmm? So we apply the formula first of all. Apply the formula. So data KP is equals to. So I don't think I'm going to. So I'm going to write the vote. I'm going to write the vote for solving. Then write the vote. And then write the vote. So KP is equals to KC into RT delta N. So we have to write the balance equation. The balance equation is N2 plus 2O2 giving 2M2. In the equation, delta N is appearing. So we have to look for delta N. Delta N here is a change in number of moles. That is the number of moles of the product minus the number of moles of the reactants. So delta M is 2 minus the number of moles for nitrogen is 1 plus oxygen is 2. So 2 minus 3. Delta N is negative 1. Apply the formula Kp is equals to Kc was 10. So Kc was 10 into R 8.31 T 373 to the power negative 1. So let's apply the formula. Kp is equals to, how to punch here using the calculator. Let's punch. How to punch. Bracket 8.31 times 373. Call that to the power minus 1 times 10. So that's the value of Kp. Kp will be 3.3 times 10 to the power minus 3. That's the value of Kp. So this marks the end of our topic 3 today. Our next topic will be Velox Equilibria. So thank you for watching and follow me on EduQs for more topics, more exercise, and more solving. I'm still coming to the chemistry teacher. See you in our next class. Thank you.